Hello, and welcome back to my channel. Today I will be talking about, in my opinion, two of the most powerful factoring theorems in all of math. These two are remainder factor theorem and rational root theorem. So I touched on this in my Vietas video, but given an equation, what exactly is a root? Well, one definition that I gave is that if x is equal to r, where r is a root, then this will be a viable solution, or x minus r is equal to 0. Now, this is when remainder factor theorem comes in. Because given an equation, so for example, I'm going to use x squared plus 2x plus 1 is equal to 0. If some value r works as x, then this equation is divisible by x minus r, or r is a root of this equation. So let's test out a value, say -1. Well, we have -1 squared plus 2, -1 plus 1 is equal to 0. So then we have 1 minus 2 plus 1 is equal to 0. Now 1 plus 1 is equal to 2, and 2 minus 2 is equal to 0. So 0 is equal to 0, and so -1 is a root. And so x squared plus 2x plus 1 is divisible by x minus -1, or x plus 1. So what we get by substituting -1 in is that we get that -1 is a root, but also that this is divisible by x plus 1. But then you might notice that for a bigger expression, there are so many values to test out, and you wouldn't know where to start or where to stop. So for example, say I give you x to the power of 4 plus 3x to the power of 3 minus 17x plus 8 is equal to 0. Well, that is when rational root theorem comes in. So rational root theorem states that for any polynomial, all of its rational roots must come in the form of the last coefficient and its factors divided by the first coefficient and its factors. So in this example over here, we know that by the rational root theorem, that all possible rational factors of this polynomial are plus or minus 8, plus or minus 4, plus or minus 2, or plus or minus 1. These two combined together are extremely powerful for factoring polynomials, especially polynomials of higher powers. So now I'm going to show you an example of when this is useful. So how would you factor x to the power of 4 plus x to the power of 3 minus x minus 1 is equal to 0? We do know that by the rational root theorem, the only possible roots are plus or minus 1. So we'll start with -1. So we get -1 to the power of 4 plus -1 to the power of 3 minus -1 minus 1 is equal to 0. Well, we get 1 minus 1 plus 1 minus 1 is equal to 0, and 0 is equal to 0 here. So we know that -1 is a root, so this is divisible by x plus 1. So x plus 1 is a factor. Next, we test out x is equal to +1. So we get 1 to the power of 4 plus 1 to the power of 3 minus 1 minus 1 is equal to 0. 1 plus 1 minus 1 minus 1 is equal to 0. 0 is equal to 0, and so also x minus 1 is a factor. So we know that these are the only rational roots of this, but we still have not factored this out yet. So what we are going to do is divide this by x minus 1 times x plus 1. Now, if you know by difference of squares, x minus 1 times x plus 1 is equal to x squared minus 1. So we're going to use polynomial long division to divide this by x squared minus 1. Now, if you don't know what polynomial long division is, that's okay. You don't have to know what it is. Just trust that if I divide a polynomial by another, I'm probably right. Alright, so now let's divide this by this. Alright, and so we are left with x squared plus x plus 1. Now, I'm just going to save us some time and tell you that there are no real solutions to this, and this cannot be further factored. And so we are done. This is equal to x plus 1 times x minus 1 times x squared plus x plus 1, with the only real roots being 1 and -1. Alright, now let's get into some problems. Alright, and so our first problem is proving that root 2 is rational. This is a classic proof problem, and there are actually many ways to prove that root 2 is rational. But what I'm going to use is the rational root theorem. The thing is, I need to make an equation first. So consider the equation x squared minus 2 is equal to 0. Now, root 2 is clearly a solution to this, as root 2 squared is equal to 2, so 2 minus 2 is indeed equal to 0. But then we can use the rational root theorem to prove that root 2 is irrational, because by the rational root theorem, the only roots we can get here are positive or negative 2 and positive or negative 1. Now, as you can probably tell, root 2 is not equal to 2 or negative 2 or 1 or negative 1. And so our problem is already solved because these are all the possible rational roots. And since root 2 is a solution to this equation, but it is not rational, then root 2 must be irrational. And so we have proven that root 2 is irrational very quickly using rational root theorem. Now on to the next problem. Alright, and now our next problem is above the whiteboard. So proving that the sine of 10 is irrational is a pretty classic problem, and I'm going to show you a pretty classic solution. The important thing here is to use the triple angle formula. Now, it's not a commonly known identity, but the sine of 3x is equal to negative 4 sine cubed x plus 3 sine x. I'm going to make another video about the derivation of this formula. It will probably be linked in the description, hopefully. So now we have to let x be equal to 10. So we have the sine of 30 is equal to negative 4 sine cubed 10 plus 3 sine of 10. Now the sine of 30 is equal to 1 over 2. Let's let x be equal to the sine of 10. So we have 1 over 2 is equal to negative 4x cubed plus 3x. We can move some terms over to the side to get 4x cubed minus 3x plus 1 over 2. Multiplying everything by 2, we get 0 is equal to 8x cubed minus 6x plus 1. Now, by the rational root theorem, our only answers can be positive or negative 1, positive or negative 1 over 2, positive or negative 1 over 4, and positive or negative 1 over 8. If you look at the graph of sine of x, between 0 and 180 degrees, sine of x is positive, and so we can eliminate all of these positive or negatives. Additionally, there are values that we know cannot be equal to the sine of 10. So for example, 1 and 1 over 2, because 1 over 2 is equal to the sine of 30, and 1 is equal to the sine of 90. So we can eliminate this and this as well. So now we are left with 1 over 4 and 1 over 8. You can quickly substitute 1 over 4 and 1 over 8 into this equation to get that x cannot be equal to 1 over 4 or 1 over 8. And so there are no rational values in this equation for the sine of 10. Just like last problem, there are no rational roots, and this is the solution to this equation. And so sine of 10 is irrational. Again, I'm going to make a video showing how to derive this equation. I highly suggest that you go and try and find it. Alright, so now let's move on to the final problem. Alright, and now our last problem is above me. The most important thing is first, we have to factor out this problem. And so by the polynomial I'm looking at, the only rational roots that I see are plus or minus 2 and plus or minus 1. To save us a lot of time, I'm going to tell you that the rational roots are negative 2 and 1. So by remainder factor theorem, this polynomial must be divisible by x plus 2 times x minus 1. So now we're going to use polynomial long division to factor out x plus 2 and x minus 1. So x plus 2 times x minus 1 is equal to x squared plus 2x minus x, or plus x minus 2. So now let's get into the polynomial long division. And so x to the power 4 plus 2ax to the power 3 plus 2a minus 2 x squared plus negative 4a plus 3x minus 2 divided by x squared plus x minus 2 is equal to x squared plus 2a minus 1x plus 1. So now we're looking for real numbers. And since 1 and negative 2 are obviously real numbers, all we need to do is look at this quadratic. So a quadratic has real solutions when the discriminant is greater than or equal to 0. So the discriminant is equal to b squared minus 4ac. In this case, a is equal to 1, b is equal to 2a minus 1, and c is equal to positive 1. So we have 2a minus 1 squared minus 4 times 1 is greater than 0. So then we have 4a squared minus 4a plus 1 minus 4 is greater than This is then equal to 2a minus 1 squared minus 4 is greater than 0. But notice that we have a difference of squares here. So we have 2a minus 3, 2a plus 1 is greater than or equal to 0. So then we have a is greater than 3 over 2, or a is lesser than negative 1 over 2. So for all values between negative 20 and positive 18, as long as it's greater than 3 over 2, or a is lesser than negative 1 over 2, then that is fine. So the zone that we are looking to avoid is between negative 1 over 2 and positive 3 over 2. And so this zone has a length of 2, while the total area is equal to 18 minus negative 20, which is equal to 18 plus 20, which is equal to 38. So we have 38 minus 2 over 38, which is equal to 36 over 38, which is equal to 18 over 19. And since these two are relatively prime, we add 18 plus 19 is equal to 37, and we are done. Alright, thanks for watching. Hopefully you enjoyed, and hopefully I'll see you next time.